Okay, welcome to IISE Transaction Webinar Series. My name is Yu Ding. I'm the editor-in-chief of IISE Transaction and on faculty of Texas A&M University. IISE Transaction Webinar Series in fall 2022 features 7 talks based on the articles to be published in a special issue of the journal. The special issue is going to appear as the first issue of 2023. Today is our second webinar in the series. And we are fortunate to have Dr. Jianjun, Caroline Stewart Chair and Professor of IISE at Georgia Tech to be with us today. Professor Jeff Wu once said, Jianjun is the most unusual engineering professor I ever known in my career. And I have known Jian since 1998 and had the good fortune to be under his supervision in my doctoral study, and I agree wholeheartedly with Professor Wu's statement. If you think about it, Jian started the quality science revolution some 25 years ago and caused the paradigm shift to the quality science and reliability engineering research landscape. Today, when we do quality science and reliability engineering, the concept, the philosophy, the approach, the impact, even the feeling, and it's very different from 30 years ago. And if you resonate with my statement, I hope you also agree with me that this difference is due to Jian's contribution and leadership. The new concept and philosophy are embodied in the development and the deployment of IPQR methodology. And this is precisely what we are going to talk about today. Jian has a long list of accomplishments and recognitions, and including being a National Academy member and the most recent winning of the Schuhart and Box medals. If I go through the whole list of Jian's accomplishments and honors, and we won't have much time left for Jian to speak, I know the audience are here to hear him out, not myself. So let's get to the topic quickly. Recently, Jian has been giving talks on the topic of IPQR, in the QSR webinar series, in the University of Hong Kong's leadership webinar series. There are recordings of those talks where the audience can watch a conventional slide progressing webinar. So because of that, and for today, we decide to do something different. And what we decide is to do away with the slides and the equations. It's going to be a conversation with Professor Jianjun. Okay. In the past weeks, many of you submitted questions, and I wanted to take this opportunity to thank all of you for gathering and submitting questions. The questions are arranged in 3 groups, and that's going to be the main part of today's conversation. The first group talks about the historical development of IPQR, and the second group talks about the methodological features of IPQR and its relationship with other schools of thought. And a lot of people also ask for Jian's advice on various professional and career issues. And therefore, the third group is a set of advice-seeking questions. Okay, so let's get started. Jian, are you ready?
Yes, I'm ready.
Okay. All right, okay. So let's move on with the first group of questions about the historical development of IPQR. And the first question I want to ask you is, what does the IPQR stand for, and how did you come up with that name? I recall when I was a student in Michigan, you often joke with us, IPQR pronounced as the ipchi, and very similar to that Korean dish, kimchi. So you said that's how you come up with the IPQR acronym. I know that was just for fun. So can you share with us your thought on coming up with that name 25 years ago?
Okay, so IPQI, really the meaning comes from the word in-process quality improvements. So talking the in-process quality improvements, the other words are not in-process quality improvements. This is more like the assessment of the quality control, quality engineering methodologies 30 years ago. So look back 30 years ago, if you study quality, what kind of topic do you try to study? So basically, there are 3 topics mainly. One is the design experiments, try to design the product process robust to disturbance. The statistic process control or statistical quality control, accept sampling, try to study the quality, process in control, auto control, how to take sampling, accept the sampling for the final product check. And the total quality management is the third aspect, which is emphasize the management aspects, the supply chain management, the awareness, training, and so on. So think about these three quality control aspects. One important aspect is missing, is what's happening during the manufacturing process, because something may happen which not anticipated. So the robust design may fail. And something may happen, the defects will occur. So the SPC, accept sampling, check the product, the defect already occurred. The total quality management makes the awareness management aspects, but cannot prevent what's happening during the manufacturing if something wrong. From another aspect, you can see there are lots of sensing already implemented in the machines. All the automation, the motors, the pressure, the vibration, those kind of things sensors have been installed. All the sensors are used in automation, in machine control, machine condition monitoring, but not linked those information with product quality. So there's the opportunity. We focus on the in situ sensing signals, but link this one with the product quality and improve quality. And also, if something happens in the manufacturing process, we can quickly find what are the root causes by use in situ sensing. We can use control capabilities to make compensation to avoid the defects occur. So this is the idea of IPQI, and also why 30 years ago we proposed IPQI as another quality control methodology to enrich the quality engineering field.
So I can see the IPQR, the IP part is very important, right? The in-process part is differentiating that the overall concept and methodology from whatever the methodology has been used at the time when IPQR was initiated.
Yeah, so that was a motivation in that time.
I see. So you partially addressed the next question I'm going to ask you. You give this kind of academic background of when the IPQR was development, but I also want to ask you about some of the societal background, right? The IPQR was developed about 25, 30 years ago. And, I look at the audience, I think some of them was probably rather young at that time, and some of them probably was not even born at that time. And so can you offer some of the societal background that 30 years ago, which motivated this, the new methodology development?
Okay, I think like anything that be started or be potentially be successful, there are three components are very important. I say in Chinese, it's called as 天时地利人和. So in English, the translation should be timing, environments, and people. So I think those are also applicable to the IPQI, why this started in early 90s. So in that time, so talking about the timing, the US quality product is far behind the competitors. For example, the automotive industry, late 80s, beat by Japanese very badly. Japanese perception of auto industry is much better quality-wise than United States, and lots of company, United States big three, suffering a lot. And talking about the car body, automotive body assembly, the Japanese Six Sigma is 2 millimeter variation, the largest variability. American typically 8.5 millimeter and above, so much behind the world, and the European countries about 4.5 millimeter. So this is make the timing American need shake up to improve quality. And the environments in that time also related to the first one is in late 80s, early 90s, a company introduced inline optical coordinate measurement machine. So the Cadillac bought the first system, Chrysler bought the first system, and the inline OCMM is able to measure every car body fabricated with 130 points on the body in white. So this is a revolutionary data acquisition capabilities compared with the old ones, use the traditional CMM. The traditional CMM get 2 car body per shift, 8 hours. And the OCMM measure every car body for 400, each one more than 100 points. So because of this technology capabilities, there are a lot of data coming in to the fabrication, to the CMM, to the car body assembly shop. However, conventional SPC does not work. If we monitor each variable and 130 control charts, definitely there are some points in control to control. And according to the quality control training sometime, if you see control chart out of control, you should shut down the line, find the root cause. Because of this, and because OCMM measures so many points, the car assembly plant cannot keep continuous production if you use SPC. As a result, they shut down the line. So the technology is available, but the data analysis is not available sometimes. So in that time, I was lucky to have a Professor Sam Wu as my PhD advisor, and he introduced me and gave the opportunity for me to work in the assembly plant to help to solve the problem. And also with my own background, this talking the people side, with my own background, I had training in automatic control in bachelor, master, or multi-PhD in China, and also in manufacturing mechanical engineering in Michigan. So this kind of background give me capabilities to understand the manufacturing process and also understand the data analysis aspects. So combine these 3 aspects, there is a need for quality improvements in automotive industry, for the body assembly. There is a capability for inline sensing, for the OCMM, for the car body. And also with my training, I can do better job. So I initiated this work. So it's more like background, how they started in early 90s.
I like the way you anchor the development on 3 important aspects, right? 天时地利人和. If we say that in English, it's probably the societal need, motivation, the technology, enabling technology appearance, and the people get together from executive and scholars, and then to make it happen. You kind of nicely describe the type of the picture 30 years ago. Can you allude or elaborate a little bit further? How does the IPR research and implementation evolve over the year, right? Still along that 3 dimension, the sensing technology, methodology, manufacturing system, and as well as like the people's methodology or the skills evolution over the time.
Yeah, I can try to say a little bit. Like earlier I said, because inline OCMM introduction to the assembly, we start this work. And talking about the data acquisition aspects, the technology aspects, the sensing capability really evolving significantly in the last 30 years. So start from single sensors, measure the individual variables, go no go gauge, the continuous variable, and functional data. And functional data for single sensor and the multiple sensors become a multi-channel functional data. And recently the image, the video, high resolution video signals become much more popular. And the video, functional data, different type sensors together collectively measure the manufacturing, leading to heterogeneous high dimensional data. So those kind of opportunities are evolving from over the years. And also you can see it become more and more challenging for the data analysis, data analytics aspects. So from the data analysis aspects, the evolving from very beginning with the statistical process control, distribution, and then multivariate statistic control, multivariate analysis, and then functional data analysis, wavelets analysis. Those are evolving from the early 90s to later, right now we see machine learning techniques, the tensor-based analysis, tensor regression, and AI, So those are the different data analysis capabilities developed with the sensing technology. And at the same time, the manufacturing system is also react to IPQI. We start with assembly problem, then machining problem, then stamping, forming applications, and then the multi-stage steel mills, the rolling process, the solar cell, semiconductor manufacturing, Boeing, I mentioned company name, that's okay. So the airplane, aerospace. So all those ones, there's the need for IPQI. And also IPQI evolving from single machine and then multiple machines in your segments, and then to the whole system, and even to the whole plant or multiple plants. So that also evolve the in-process cost improvements. So in these aspects, we can see the IPQI is evolving and becoming more and more important, and it really has a rich research components and also potential impacts to different industry sectors and in different scale. I'm talking single machine, multiple machine, plants, supply chain. So there are lots of opportunities for this to go further.
I think in describing this part, you already answered actually my next question, which is about to ask you the major impacts of IPQR, right? You mentioned start with the assembly process, goes to machining, forging, and other kind of metal processing, even to aircraft assembly process. Do you have anything to add on to that? Any kind of specific example you like to providing? I know there are some probably like proprietary information you cannot offer, but if you said that is pretty much covered, you plan to say, we can move on to the next question.
Yeah, I cannot say some information not in public, but in public information, the impact of IPQI. For example, Jefferson now, the assembly plant of Chrysler, use our data analysis techniques, basically stream variation concepts. The quality of body assembly achieved 2 millimeter in the end of 1992. So this become a national news in many newspapers talking about this. So the very first time American body assembly achieved world-class quality. So that's this in public domain information. Another impact in the public domain information is a leading company for inline hot rolling process. Lead projects, I'm co-PI of the project. That was funded by Department of Energy. And the project was for 3 years, and the methodology developed, implemented in more than 50 steel mills worldwide, more than 15 countries. The Department of Energy had a follow-up, third-party follow-up to evaluate the projects, what kind of impacts, how these projects evolve to the society, economic impacts. The study shows because the inline sensing and defect prevention in the hot rolling process can avoid more than 2% of defects occurred in the reality. And hot rolling is the heavy energy consumption industry. Because of this defect prevention, each year they can save $100 million cost and 50 ton CO2. So this number from the third party from Department of Energy is available on the website. So those are the kind of impacts we can see through IPQI to achieve defect prevention. And then we can save lots of energy, material, manpower, and this leading to economical and social issue impacts.
Speaking of Jefferson North, you recall actually I went there for quite a number of years. Actually, James Kuhn during probably 1 or 2 years, so he went there together with me. And,
yeah, I follow Dr. Ding and another colleague and the Zhang Rong, right, together. I just went there for a couple of weeks, right?
So you guys are the doer to make this happen. I'm the person talking about it happen.
But that leadership is very important, and also the opportunity is my first time to work in real auto the workshop in the actual automobile manufacturing company. That's not easy. It's not like every day you have the opportunity to go over there. Okay, so Jian, you talked a lot about all this kind of collaborations with industries, company on the IPQR related research. How do you convince them to share their data and work with you? How do you implement your research methodology into practice? Is there anything you can share with the audience? There's actually another question later in the advice seeking part, and some, especially the junior faculty, specifically want to ask something follow up. But for the time being, if you can think of something limit to your response to, like when you were doing that, right? How did you get it done, right? Sometimes we know it's not easy to work with industry.
I think this is really a big question. There are many ways. So each case is case by case, is individual aspects. If I try to summarize the different groups, how I work with the industry and how this started, I think one is try to work with a small company, the in situ sensing company. For example, in the assembly, I work with the inline optical CMM company. So they are the best company and the only one in the world at that time. I mean, even now, they are the leading company for inline measurements of OCMM. They generate lots of data, but how to use it effectively is a question. Same thing, I work with the leading company in hard rolling process. They can have sensors to measure the hard rolling parts up to 400 feet per second with temperature 1600 degrees. This is the only company have that kind of sensing capabilities, no competitors. The other company will be slower and lower temperature. And another example is I work on the foaming stamping with the signature analysis. In the world, there are, I should say in America, there are 3 tonnage monitor companies. And I consult all 3 and try to find what are common issues. Use a tonnage sense, how to use this effectively. So for this inline sensing company, they have the customer, they have the real data, and they have the motivation to use their sensor better. And from their customer point of view, they bought the sensor already, typically for some simple reasons, quality inspection, rather than monitoring diagnosis, defect prevention. But if we can accomplish this one, their customer will be happy. So with that kind of a teamwork, we can work together on the problems that they interested. So the second aspect, this first one, work with the small company on the sensing company. The second one is work with the consortium, especially formed by the leading OEM. For example, Big 3. Big 3 formalized the auto body consortium. I was the chief scientist of the auto body consortium. Because there's a national need at that time, the automotive get behind in terms of quality. The Big 3 had the need to do this. So that's their motivation. But by working with them, they are the big boss and they have lots of suppliers. Like near zero stamping, I was responsible. They get 64 companies of their suppliers. They said, you have to work with Jianjun. We want the stamping industry shake up and improve quality, get a near zero variation. So this come from the big boss, Big 3. All their suppliers, so from the CEO, the chief scientist, will listen. So I can easily schedule meeting and define the problems. So that's leading to this 5 years ATP projects, $19.7 million with multiple companies in the industry. So this is another way to work with the industry. And in both cases, because the industry spend money and they have motivation to implement this in the reality. So as a result, we can formalize the team and work on those kind of problems.
You said 3. There's 1, 2, and you have one.
I thought I should finish. Okay, I mentioned 3. Third one. The third one is there's like IUCRC, Industrial University Corporation Center from National Science Foundation. Those are the typical companies that get together to work on one types of problems, all those companies interested. As an IPQI types of research, you can imagine we can contribute on almost all industry sectors and all problems, not necessarily manufacturing, some sensing, some verification, quality material, we can contribute as a data analytic tools. So work with IUCRC, you can get access to the industry. And even better is the ERC, Engineering Research Center. If we can work with them, we can work with the industry, and also the consortium, industry consortium, that also helps.
Well, we'll come back to that question a little bit later in the advice-seeking group. But let's move on to the methodological feature discussion about the IPQR. And from your early discussion, I gathered you already have a big data problem even before the term big data was coined. And but on the other hand, I think the IPQR emphasize more than big data, right? There's a very important aspect about control and automation. So how does the automation play the role in the IPQR research, and how it's related to automatic control in EE or in mechanical engineering?
Okay, automated control definitely is very important in all manufacturing applications. So all machine basically use automatic control. In ME, in EE types of automation, which we taught and learned, is more focused on machine. So if I design a robot, the robot can put the parts into position with XYZ, zero variation, zero on the target. That's good machine. I design a motor with the shortest time to achieve the stable speed. That's a good automation. So all this automation focus on machine, device. That's EE, ME types of automation. And for IPQI, we focus on quality. Quality are delivered by the machine device. So you can imagine, I have a device, I can get the RPM 500 on target, perfect. I have a material handling with position, perfect. All those perfect automation applied to a quality with the combination may not leading to the best quality, because you could be the siting decided wrong. So yeah, and also there are some disturbance to the product quality beyond the machine level. Use in other words, if I have a feedback loop for the automation, that endpoint is the process variable. And the process variable impact on the product quality variable. So between process variable and the quality variable, there's another dynamics, another model has big impacts. That's one thing. So IPQI focus on quality. The second thing is the quality is impacted by multiple machines, multiple devices, not just one. So in this situation, the quality response with the multiple inputs of multiple devices. And there are the dynamics between this one and the quality. Further, any manufacturing process is a multi-stage manufacturing process. I mean, there's no, other than 3D printing, even 3D printing, you produce some parts, still need multi-stage later. So in multi-stage manufacturing process, we care about the final quality of the product. There is complex interactions among the machine device along the production line. The combination effects leading to the final product, good or not good. So by saying this, I should really develop new types of model to model the quality response with all these control variables of the machine. So the machine automation is a subset of the quality response. And from another aspect, when we measure the quality, it's different from automation. Most of automation have continuous variables as a response. So you can use a Laplace transform, discrete differential equation, and dynamics equation to describe. So more, I want to say more like standardized homogeneous equations to describe. But for quality response, it can be a go, no go, can be text variable, can be the continuous variable, can be function curve, like a gas cylinder. You see what's the gas cylinder. is a functional curve, can be an image, can be video signals. So with those as input, as output of quality measure, how to model this automation for quality. So that's a absolutely new research area. And also considering the quality measurements are not like automation, which is a uni sampling interval, most of cases. Quality measure is completely different. High frequency, low frequency, non-uniform frequency. So those are the realities of quality measurements. So how this reality translates to a model, and we can control the process variables leading to the best quality with a multi-stage manufacturing system. So that's definitely deserve more research. We have done something, and many of you also work on this, but this is the rich research environments deserve lots of study.
Wonderful. You mentioned about 3D printing. I think 3D printing actually is a very good example of multi-stage because you are layer by layer. The previous layer, if you do something with the bias or variability, it actually cascade, right? It propagates through, and it's to some extent, I think, even better example than the subtracting the machining process. So another question related to the quality part, right?
If I can, you mentioned 3D printing and it's multi-stage, definitely. And also we're talking about the quality as a response for this automation. Since you talked 3D printing, I'd say another observation idea. So in the 3D printing, there are lots of sensors for the process variable. Definitely there's a quality response. And this is one excellent opportunity for IPQI research. At the same time, I just mentioned quality as a response makes the automation for quality as a new research area. Quality is one step further from the automation. I said automation generates the force, the position, and then leading to quality. I like to say 3D printing is not just printing the parts, but printing a product with a certain function and to be used somewhere.
Right.
So in other words, if I do SPC, monitor process stable, that's not sufficient for 3D printing. If I use 3D parts quality inspection, dimension, force, dimension, those kind of variables, that's also not ultimate objective of 3D printing. 3D printing, go to another place like this cup. If I use this one as a pillar, so this force is very important, right? This is a structure. If I use this one as a shaft, I rotate this. This kind of a property is very important, right? So in other words, control the 3D printing, but considering the quantification of the parts. That is process quality, conventional way we think about the dimension, those kind of things, smoothness, and then how to use these parts. So link this one to in-process variables. If you can think about further, where to use it, you can think further. That kind of way of thinking should be extended. And once you go one step further and further, there are tons of research challenges and opportunities. And at the same time, there are lots of social impacts, if you can do it.
Right. So if I can summarize what you just said is, in some of the conventional automation and control, they directly control certain kind of process variable, right, for certain kind of process condition. But the process variable process condition is only a proxy to the final product functionality. They may relate it, but they are not really directly, they are not the direct target. So the big gap to be narrowed by the IPQR methodology is try to say, instead of control the process variable, you still need to control those, but you need to keep that direct product functionality in mind, and then to put that in the feedback loop of the automation and the control. So the quality part, the in-process, which is really targeted on the QI part, right, the quality improvement part. So that 4 letters, you cannot really eliminate any of them. It's not only in process, it's not only quality control, it's really in process quality improvement.
So that's a very good summary. One more point is you can control the process, make the final product functionality acceptable. And at the same time, if certain particular functionality not very good, the IPQI research should lead into particular root cause. If you have 100 variables in the process, one functionality not good, within the 100 samples, I mean the variables, maybe 138 are the problem, are the cause. So those kind of information also very important for quality improvements eventually.
Okay, so we talked a lot about the IP part, the in-process part. And let's talk a little bit about the QI part, the quality improvement. Actually, you allude to that part earlier when you give the historical background. You said there's existing methodology like DOE, SPC sampling, and total quality management. Some people may ask, many companies actually really manage their quality without using complex statistical method. And how do you see, how do you convince that those set of companies, the total quality management and the difference between that and the IPQI, and why they probably should think somewhat differently and consider IPQI in addition to quality management?
And first, I say total quality management is really important in quality science. That give the awareness of the quality, give the assignments, give the policies, the rules of all these quality holders from different levels of a company. But to me, this is more like a training, a policy, a checklist is not involved what's really happening during the manufacturing process. The total quality management is implemented in many applications, and especially for some satellite, so aerospace, those kind of product, the quality is very critical, and you cannot allow to have any defects. The total quality management have different detailed policies to ensure every device, every components, they have a checklist, they have different aspects. They have 2-3 people sign off of the product to make sure this one is correct. So these are very important aspects. However, if a product not good, you have a defect, you don't sign off, you return this one, throw away this one. How to avoid this? If you don't use the in-process sensing, in-process variables, you see the quality is bad, you cannot find what's the problem. So I say IPQI is the one addition to this, I say early has 3, right now the 4th components of quality engineering tools. So IPQI can first try to prevent defects before arrive this sign off step. And also if indeed this have defects, IPQI can help find the root cause and eliminate next round. So IPQI and quality management are not competing each other. They compromise each other in the total quality engineering field. That's how I see they work together. And also, in-process quality improvement IPQI should be part of the total quality management tools in the toolbox. So this, if you say right now you have different awareness, different checklist, the IPQI capabilities outcome should be another checklist in the quality management.
Great. So the 4 tools for the audience is DOE, SPC, total quality management, and IPQR. And so we talk a lot about the data right now. I believe right now it's pretty clear to us the data availability, the enabling sensor technology bring the data for the IPQI development. I want to ask a kind of a question in the other way around. Does the IPQR concepts and the IPQR method actually in turn change the way how quality data collection process has been going on, or the advise the sensor placement strategy, for example, in the multi-stage manufacturing systems?
Yes, I think so. Definitely. In fact, one of your research work is sensor placement for automotive industry. So this work already changed the conventional sensing or sensor placement objectives. Even today, most of the objective of sensing in the quality management, quality is product quality inspection. Use another words like body shop. In the end of the production, you have a car body before go to the painting. You check the dimension, the surface conditions, and compare this one with the design intent to see this one is a good product, bad product. So this is I name product quality oriented measurement strategy. So for IPQI, we want to change this one into a combined product quality oriented and process oriented quality measurements. Because if we can control the process and the process variables are very good, the product will be good. So instead of only measure the product quality, we also measure the process variables and also product in the intermediate position. So this distributed sensing strategy can reduce number of sensors, can find the root causes, can have early detection of anything wrong, and can help prevent the final product goes bad. So this is, I say, the philosophy shift from product-oriented to process-oriented. That's one point. Another point is in the engineering system, there's a causation, cause effect. So based on the cause effect, we can get a probability network model and the causation model. From the causation model, we can decide where to put the sensors in this network, which node, and also considering how much delay is tolerated, what kind of sensitivity we hope to get for the mean shift, for the process change. By borrow the causal effects inference model, we can decide where to put sensors and what kind of delay and what kind of sensitivity analysis for each node. And this also changed the sensing placement strategy. Yeah.
I want to add one point to what you said. It also tried to reduce the sensor cost. It's not like the more the better, because you need to maintain the sensors. And some sensors actually gone bad. If you have 100 sensors versus 20, the 100 sensors is a whole lot harder to be maintained for them to function all the time, and also cost more. Right? If a sensor give you a wrong reading, actually sometimes it's more harmful than because you basically lost your eyes and ears in the process.
Yes, thank you.
Okay, so next question is a little bit more detail in terms of currently people talk about machine learning models, data-driven models, the very issue of model complexity versus the interpretability. For those kind of complex model, nonlinear models kind of come to the very front of everyone's thinking. Does IPQR have this kind of trade-off, right, between the model complexity and the interpretability? And if so, how to balance between these two choices, the complexity versus the interpretability?
I think, okay, that's my opinion. I say one day I sit with a CEO of a major semiconductor company. We sit together in a roundtable meeting, and he said, "Jian, I know you're doing data analysis, data fusion for quality improvements." He asked me what I teach. I said I teach this system informatics control, statistical method for manufacturing, and so on. And he said, "I have one question. I heard from computer science guys saying we just only need to teach machine learning. The statistic tools no need to teach anymore, because machine learning can tell you everything, and you put this one, you don't need to understand the engineering principles. You can scratch a quick results, which is pretty good if you have sufficient data." He asked my opinion, and I told him, I said, I disagree as an engineer, because an engineer has the engineering principle. They have many years knowledge how to develop, understand the engineering relationships. I say machine learning is very important. It can leading to discover something and very select many effective tools, but cannot neglect the engineering aspects of this. And then he said he totally agree. He doesn't want to check with me, my opinion. So by saying so, I think as an engineer, the model complexity is something we may have to adopt. If there's a simple model and more complex model, for sure we use simpler ones. That's no doubt. We increase complexity, try to fit the data better, try to make the prediction better. At the same time, we should really emphasize engineering interpretation of the model and the result and the input. So because we have lots of engineering understanding in the systems, that's one. The second one is that when you talk about implement the model and communicate with the doer in reality, it's very hard to convince an engineer to follow a very complex model, and the engineer does not know where that come from. So for example, if there's a complex machine, through your model, you say the machine should set in this 1, 2, 3 way. I don't think the engineer will listen to you. I mean, no matter how good you claim that the model claims. So I think try to find the balance between these two is very important, and always make efforts to incorporate engineering knowledge when we use machine learning tools. That also helps, and lots of research has been done or being done. Try to use the physics-informed machine learning. I think that's really something we as an engineer should further develop. And I don't believe a pure machine learning expert can really develop independently for some manufacturing applications, especially manufacturing applications do not have that kind of data. They have unlimited, not bounded solutions. And any variable change can change the system completely different. And sample size is very limited. So in this kind of situation, we should use machine learning AI tools, but combined with our engineering capabilities to develop something useful. That's my opinion.
Yeah. I want to add one point to what you already said. I completely agree with whatever you have been saying. IPQR, for example, one of the foundational model, the state space model, is not a purely data-driven model. Actually, the state space model, by and large, is a physics-driven model. So the interpretability of that model is very well, and because you measure the dimension of your parts, the parameters in your manufacturing process, and then use those kind of physics meaningful parameters, and then come up with the state space model. So for that matter, even the model looks sometimes could be complicated because the product is complicated. The interpretability of that model actually is very good because they have physical meaning behind almost every single parameters in that model. Because I helped to develop a part of the model, so I know that part pretty well. Okay. The last question in the second group of the methodological feature ask you about the new era of the data science and AI, right? When you start doing this IPQR part, even big data is a big part of that. Even data science method has been used systematically. But at that time, those words has not been used so broadly in the engineering field as for today. So you also mentioned the relevance of IPQR to like 3D printing in answering one of the questions earlier. And what else do you see the new opportunities? And do you want to elaborate on that new relevance, the new opportunity for IPQR in the current day?
I think sometime last year, or early this year, I forgot. I gave a seminar in Hong Kong University, the IE department series. The title of the seminar is Machine Learning Enabled In-Process Quality Improvements. This talk, the video is still on the YouTube. If you search Jianjun on YouTube, you probably can find this talk. Over there, I gave a few case studies. I said, without machine learning tools, those results cannot be accomplished, or those problems cannot be solved. So interested audience can Google and watch that one. So I'll give detailed explanation why. I say a few words beyond that presentation or some new work we have done or being done. So I just see the problem. Okay. So in semiconductor manufacturing, you can have 100,000, I mean, I say 20,000, 30,000 quality variables, features, and you have 100,000 variables may impact on this. So if there's something wrong in the quality, what are the root cause? I mean, what are the potential root cause? Use in other words, there are so many variables as a response. There are tons of them. I mean, this is a tons already quality. There's tons of product variables. How to find the association between them? I mean, that's one open question. So this need those kinds of efforts to fund it. And also in semiconductor manufacturing, I heard, I mean, I read some articles saying 80% of the data collected will never be revisited in reality, in practice, because data is huge, and how to revisit to find the information, that's a question mark. But revisit is very important. Same thing, Andy Wang had a paper recently talking about holistic retrospective data analysis, not that high dimension, but also focus on the rolling process based on historical data, try to find what's happening in the time period, what kind of events, which variables involved, how those events pattern related. Those kind of research is not IPQI, but also data analytics for quality improvements, because by doing so, you can find out historically what happened, how to avoid this one, how this particular batch of the product quality aspects, issues for the customer. Okay, some other ongoing work I cannot say, but there are lots of opportunities use machine learning can accomplish something we cannot do in the past.
Okay, well, wonderful. That concludes our second group of discussion of IPQR methodological features. And the third group is a set of questions, may not necessarily directly related to IPQR, but it's a lot of questions people have been asking or contributing to ask you about some advice related to career and professional development. And the first question is actually related to the student and the educational philosophy, right? I know I'm one of the graduate students participated in the development of IPQR, and I benefit from that experience a great deal. And so people want to get your feedback and advice and for the how to work with graduate student, and basically it's the general educational philosophy you have.
That's a big question. We can talk this for, we can discuss this for hours. I think talk about this one. From my own experience, work with PhD students. First, I try to identify students who is really motivated to be the best. I'm not saying the student eventually can be the best, but the student like to be the best. Also, that involved with the advisor during the process, try to motivate the students to do better. I think that's one thing. Another thing is try to understand students' capabilities, what kind of background, and discuss with the students, try to find a topic which fit the students' interest and also desire. And another thing is to work with PhD students is every student is different. I mean, some of you are senior PhD advisors. You probably agree with me. Every student is different. Some student has a different strengths and weakness. So we understand what strengths, what weakness, and treat them as a partner, friend. We show the respect. That's very important. And also by working with students, of course, each one is differently, but give students a higher expectation, only one level higher than the student capability. I think this is very important. After you understand students, you give them some tasks, and they can do level A or level B, level C, that doesn't matter, that's capability. But you just add plus, say this is your expectation. A plus, C plus, B plus, so whatever is the capability, add plus. This will ensure the students work hard toward the goal and also can accomplish the goal. Slowly, the students will be more confident and accomplish much more. I think that's quite important. Yeah, I just stop here. I can say much more.
Yeah, I can recall when I was a student in Michigan, you probably applied that to give the student some work slightly beyond their capability. You apply that philosophy, at least to me, because I can feel there are certain things I don't really know what to do initially, but turns out to be a very good training experience. And it makes me feel really good when I was able to accomplish that, even partially.
I just give one specific example along this line. If you look at my CV, there's a publication list. And then you check each student's name, and then check the student's first paper, second paper, third paper. You probably can see the very first paper is not the best, the quality-wise, compared to the second, third. But my opinion is, if a student work on a topic for a while and able to publish the first paper, not the best, but is adequate, I encourage the student publish this paper. This is not just paper, but this is a milestone for students. And if students can publish this one, they're really motivated to continue to work on the second one, third one. And during this process, they can improve much better. However, if we say we hold the same standard, the first paper should be the same quality as a fourth year quality. The student may take a while to publish this one. And during the process, the student may already either give up or already depressed to say, oh, I cannot make it. I mean, this is a simple example to say what's the expectation and what's the way, along the way to advise students.
Okay. So we are on top of the hour. Like I said, we're going to go on a little bit longer. If your time allows you to stay, you are more than welcome to stay. And we also, because Professor Xu said he's going to be available even after the session. And so we're going to have some open discussion after that. Okay, so let me move on to next question. We talk about the working with industry. So one of the specific questions from a group of junior faculty, their question is like, what if I don't have a small company right now can work with me? What if I don't really have that kind of automotive consortium, auto body consortium? I can be part of that. And what is the general advice I should approach industry member?
I think there are many ways to. First, you should try to understand the need of the industry sectors. So in the industry sectors, what are the important problems? You can find this from the roadmap of the industry that's available from many agencies. You can find it from the call for proposals, Department of Energy, Department of DOD, and the NIST industry consortium. They have a call for proposals. Those are the sources to understand the problem. Of course, if you have access to a consortium, to industry members, ask them, what is the top 2, top 3 quality issues, productivity issues, what bothers you? And you also ask if these top issues happened yesterday or has been for a while. You want to study problems, bother them for a while, not yesterday come up, tomorrow they solve. So this is not a problem you're working on. So after you know this consortium, the problems, you have some understanding. You try to see who is the holder of those problems. You try to go to the industrial symposium. I say not informs, not necessary as ERC, but something with wind energy, with engine, with transmission, those industry types of companies, forming association, holding. Go there, see who is the holder, and then you talk to them. And then you offer to work with them by their data, but not ask money. I think that's the key. Don't go there, ask money first. Say, I can solve your problem. You say, okay, I have these ideas. You have these kind of capabilities. How can I work with you for free for this one? We just work together. And then there's a chance they give you data and you work on the problem. When you work on the problem, you should focus on solve the problem first, not develop methodology first. Of course, you can develop methodology is great, but solve the problem, make the industry believe you can work with them, and then you can think about if any potential funding possible. If this is a big company, if this small company, can you team up with the company to write SBIR or get funding from the government agency? If this problem is a long-lasting, important problem, I'm almost sure many funding agencies are interested to solve this problem. Not the industry, all the consortium, all the government agencies. So I think that's a road path to start collaboration with the industry, and also work with industry. I always say you should rely on two legs. One leg is solve the problem and don't think about methodology. Find the simple, best way, effectively useful. The second leg is based on this problem, how can develop generic methodologies? And this methodology can lead into the best publications, the long-lasting research topics, may or may not be implementable in this particular application. So you need to keep this in mind rather than think about, oh, no research topics, not interesting. Any problems you can put hands on, and if this one is the important long-lasting problem, I guarantee there are some research issues. Otherwise, there are smart engineers already solved the problem.
I can provide one example supporting what you said about once you have some kind of good result solutions, not only you should go to our own professional conference, you also need to go to some of the industry conference or industry related conference, and where the impact will be appreciated. And I remember, this is actually before I know your advice, but even before that, I went to one of the Turbo Expo conference, which is ASME conference. They have this wind energy track. The reason I went there at that time really is because of it's in a nice place. It's somewhere in Germany. So I want to go to Europe just to spend some time with my family. But after I presented one of our early work on the wind turbine performance evaluation, one of the German company, the technical director, approached me. And he said, do you really can do what you claim you can do in that talk? I said, I believe so, otherwise I wouldn't begin with the talk. And then afterwards, they signed NDA with me, provide the data, we did the case study. That actually is a very important step leading to further industry collaborations from that point onward. And we even published that joint case study with that small company in 2017. So I do believe that sometimes generate the opportunities sometimes you don't really foresee. So Jian, you have a highly successful career, right? The very high quality scholarly work, real life impact. Many researchers dream of being able to do the same, right? So for many of the young researchers, even for researchers like myself, who stayed in the field for a while, right? What advice do you have, for them to get started, right? What advice do you have for even students and who will become our colleague in the coming years and who are interested in studying this industrial engineering and operational research and the data science, the problems in the future?
I'm not sure I'm a highly accomplished researcher or scholar. I think I'm lucky and also really because of the former PhD students, sponsors, they are very, the former student very capable, the sponsors very nice to me, so I can do something on the research. For junior faculty, I think that for any faculty members evaluation, the three aspects, right? It's research, education, and service. Just briefly, if I say research, for sure we need to identify important, long-lasting, potential big impact research topics. And then how to evaluate the research topic is good or not. I've said that some of you heard of my talk is 3 pillars. If you can get one of these 3 pillars, that research topic can be good, potentially good. One is important new problems. So the problem is new. For example, I just say if a 3D printing considering in situ quantification for different mixed materials, I think that's a challenging problem. That's needed and also challenging. So new problems, new tools, just tools, new like if in early years, the advanced statistics is new in the early 90s. The wavelets was new to quality improvements. The tensor, currently tensor-based regression, the heterogeneous data modeling, those are the new methodologies that could be used for machine learning as a methodology could be useful. So that's this new stuff work on use this one to solve problems and the corresponding problem. I think that's important. And the third one is new sensors, new actuators. So when I work on many research topics, I start to use the inline OCMM. That was new, so that was not capable before. And the hard rolling, I talk about inline sensing for 400 meters per second, 1600 degrees. That's new. Nobody has that kind of sensing capabilities in the world. So I work on this problem, definitely important problem. And so those are the, I worked on dynamic balancing as project. Sometimes the inventor of a balancer is a new actuator, never existed before. So working with this one on the dynamic balance problem, that is important. So these are three pillars, new problem or new methodology or new sensing actuator machine capabilities. If one of this, I mean, two of this is even better. I think that's a good research problem. And also try to study some real challenging, long-lasting problems, not improve another paper. Another paper assume normal distribution, you put this as a Weibull distribution, I just say. I mean, this also definitely contribution, definitely publishable work, but this is the continuous improvements, in my opinion. It could be very challenging also, this research topic, but different from certain research area, important problem, you start with a mathematical formulation, and after this formulation, many people study further. I think that's, to me, that's an important problem. Even the first mathematical model for the problem is has a lot of assumptions. That's okay. You are the first one start this one and keep working. And I think that's for the research aspects. Education for junior faculties. It's important after you have some paper, some research. Surrounding your research, you offer new graduate course. I think if you can offer a graduate course, you can access with the new students, try to identify some potential students work with you, and also train them before they work with you. I think that's a good aspect. Of course, I mean, many slogans, you'll be the good teacher and something, of course, you should do it. And just say specific ideas. Offer some new courses combined with your research. The graduate level courses, I think that's very important. The service aspects after the third year, I say, probably I would say the third year, try to do some service in the professional society, start to organize sessions and be the council member or something. So basically become visible. You don't want to do this in the first year or second year. You should really develop something belong to your own. Means you work on this research, you name associated with certain research, and by the third year, you can get more visibility and people know what you're working on. If first year you get visibility, people still don't know what you're working on. That's too early, in my opinion. So all those are important. Very strong, solid research topic. So education, get students work with you, and the third year to get some visibility doing professional service, and visit some other universities in the fourth year, fifth year. I think that's also important. Is this too specific?
No, I think that's great. You're talking about do's, right? What people want to consider doing. Anything don'ts? Anything like you want to avoid? I mean, the junior faculty, when they start their career, they want to avoid?
Okay. Again, this is just my opinion. I know there are some counterparts say I'm not right, but I'll disagree. I think try to work on some important problems with your own background, your own training, not necessarily 100% overlap, but should have some basis. When you select the topic, you should all write a career proposal. You should always ask the following questions. Is this problem really important? Is this problem really worth of study? No matter whom. So this problem should be studied no matter by somebody. Okay, not say something only I think important. That's one question. The second question is why other people did not study this problem before? Why I read the proposal? Why other people not work on this? The third one is why me? Why should I work on this one, not other people? I think those are the important questions. By saying this, what not to do? Don't get into something you have no idea what is it. People say this important problem, but you don't have training. And I think that's a bad situation. And try to work with motivated students. If students don't want to study for PhD or study for PhD because the person's mom or daddy want the person to study, the person does not know why. I mean, try to avoid such kind of students in your interview. Try to, work with other people, write joint proposals, but not just work with other people, always write joint proposals. You should have your own proposal and you are leading some proposal. The good balance is very, very important. And also when you have, be aggressive when you're doing research, doing the work, but not be aggressive when sharing the credits. So I always talk to my students or friends. I say, if you work with others, you deserve 50% the credits. You just ask 45%. Just stay at 45%. I think in this way, in long run, you have more collaborators. You can accomplish much more. If you ask 50%, the other people think you 45%. Then probably it's the last time to collaborate.
Right.
So be humble, and this maybe not a place to talk about this.